Welcome to this month's November 2021 version of Astronomy on Tap. We're coming to you live from Baton Rouge today. As for right now, we're still planning to reconsider our online status in the new year, but if you want to see us again in person, we really ask that you get your COVID vaccine if you haven't, and if you have, then encourage your friends and family to do the same. That would really help us out. So this month we have two wonderful speakers, but before we get started, I have to go over the usual ground rules. Number one, be considerate in the chat. We never have issues, but it's always worth saying. Number two, feel free to drop your questions for the speakers at any point during the talk, and then after the talk, I will field them to the speaker. Number three, please consider donating to our show. We actually aren't able to use our Venmo anymore since they changed up their rules a little bit, so we only have PayPal, but you're still free to use that. But as per usual, we like to add some competition to our donations. So this month we're asking you which of the solar system's 4 ringed planets is your favorite. Most of us know about Saturn's rings, but in fact, all of the gas giants have rings. So that's Jupiter, Saturn, Uranus, and Neptune. All 4 of them have rings. So we want to know which one of those is your favorite. And if you do choose to make a donation to our PayPal, do write your answer in the memo section so that we can keep track of all that stuff. Number 4, and the last one, please like this video if you're watching and subscribe to our YouTube channel because those things help us out so much and it helps us get shown to more people. One more thing before we actually start the talks is that tonight there's going to be a lunar eclipse, and so if there are no clouds in your location, you should definitely get outside and watch it, or at least look at it if you can. So without any further ado, let's move right on to today's talks. Our first speaker today is a graduate student at CU Boulder. In her undergraduate studies, she also obtained a degree in philosophy at the same time as her astronomy degree, and she says that she's donated over 7 gallons of blood in her lifetime. In grad school, she works on exoplanet atmospheres as well as working in instrumentation, and today she's here to talk to us about all of the different types of clouds in space. Here is Erica Egan.
Hello. Thank you for that introduction. So, as stated, my name is Erica. I'm a PhD candidate at the University of Colorado Boulder. And tonight, I want to tell you why I love clouds. Even though I don't really study them, I don't do them for my research, I don't do anything about clouds. I just think they're really cool. This picture that you see right here is a picture that I took outside of my office and laboratory earlier this year at about May. It's stunning. Cumulonimbus clouds that almost look a bit lenticular as well. It's a strange combination. And I've seen more types of clouds in Boulder than I have anywhere else that I've ever lived. And it inspired me to put together this talk. So I present to you Clouds of the Universe. But like, what are clouds, man? Like, what are they? Are they like rivers in the valleys of mountains that fall off into the plains and above our heads? Are they remnants of ancient earthly Leviathan that are now bound by gravity to the planet roaming in the skies? Are they puffs of cotton candy that have yet to be harvested? Or are they hard spears or weapons of the upper atmosphere defending us from alien invaders? Are they all of the above? Are they none of the above? More seriously, we know that here on Earth, clouds are typically made of water vapor. We can see them all over the world, and they're formed at many different altitudes, have different densities, and have different shapes. And they're usually indicators of impending weather. So here's a meteorological definition of a cloud: an aerosol consisting of visible mass of minute liquid droplets, frozen crystals, or other particles suspended in the atmosphere or similar space. Lots of words. Let's break it down and make it make sense. An aerosol, suspended fine particles. Now, all of you are familiar with what this means. Some examples include smoke, pollen, or mists from spray cans. Notice that the definition of an aerosol doesn't specify solid or liquid because it includes both. We might think of smoke as tiny little pieces of solid matter. Pollen is certainly a solid, and liquid droplets or mist from a canister, like hairspray, lubricant, or perfume, all of those are all aerosols. They're tiny things that are small enough to be suspended in the air. So moving on to the next chunk in our definition, visible mass. Now this one is pretty easy. The word visible meaning that we can see it, meaning that it interacts with light. And then mass is just stuff. It's physical matter. Pretty much everything you can see is visible matter. There's rubber ducks, galaxies. Most likely everything that you interact with in your day-to-day life is visible mass. If you can see it, it's visible mass. If you can't see it, maybe it's still mass, but it's not visible. Maybe it's not mass at all. So what's not considered visible mass? Something like existential dread, no matter how heavy it is not visible mass. It's not something that interacts with light. So let's recap the definition of a cloud before moving on. An aerosol consisting of visible mass of minute liquid droplets, frozen crystals, or other particles suspended in the atmosphere or similar space. We know what an aerosol is. We know what visible mass is. Let's talk about minute liquid droplets, frozen crystals, or other particles. Droplets, frozen crystals, something like snow, for example, or other particles have a range of sizes, and they can all be considered aerosol as long as they're able to be suspended in the atmosphere. The upper limit for this is about 100 microns, and it drops all the way down to just a fraction of a micron. Now, a micron is 1/1,000,000th of a meter. Take a meter, a yardstick, a meter, divide it into precisely 1,000,000 parts evenly, and one of those is a micron. Micron is very small. So some examples of particles that are microns in size. We have fine sand or salt at 50 to 100 microns. There's pollen at 15 microns, respiratory droplets at 5 to 10 microns, and dust even smaller at 2.5 microns. And you're familiar with a lot of the stuff on this list, and you're familiar that lots of these things can become clouds. We've seen pollen clouds, we've seen dust clouds. And most of these fit within the other particles of the definition, but they fit nonetheless. Finally, the last part of our definition is suspended in the atmosphere or similar space. The atmosphere, in this case, is the envelope of gas surrounding the planet Earth. It's the gaseous medium in which we all move around and exist in. It's the stuff that we breathe. It's the stuff that we frolic in. It's the thing that helps flowers grow, the gas in the atmosphere. And while atmosphere can also mean vibe or feeling or the third element in the trifecta of a good restaurant, that is not the definition that we're interested in. We're interested in the gas. So this definition of a cloud, an aerosol consisting of visible mass of minute liquid droplets, frozen crystals, or other particles suspended in the atmosphere or similar space, makes great sense now. We know what these words are, and now we know how to think of clouds. And even without that definition, most of you probably know a cloud when you see one. But it's good to have this specific definition in mind because clouds are more than just fluffy white things in the sky. Take a look at these pictures. A pollen cloud in the upper left, a dust cloud in the lower left, and a rain column cloud on the right. If I asked you to describe these pictures, you could do that. If I asked you to describe what happened before these pictures were taken and what might happen afterwards, so the time context of the pictures, you could probably do that too. The pollen cloud in the upper left tells us that it's around springtime and there was some force, be it a landscaper or a powerful squirrel or wind, some force that shook that pollen loose from that tree. In the lower left, we can imagine that maybe large sustained gales of wind kicked up dust clouds and dust storms and created that. And then on the right, rain clouds tell us that there was a lot of water above us and now it all couldn't stay there. And so it's coming down. And eventually at the end of that, we know there's not going to be water left and there's not going to be any more rain. Clouds then are functions of their environment. Something created them. They're made of matter that was in the location of their origin, and some force stirred them up. They serve as a diagnostic of their surroundings. And on some level, we're familiar with this idea already. People have been using clouds to understand and predict the weather on Earth for centuries. Specific kinds of clouds reliably form within specific altitude ranges, and their formation serves as a diagnostic for what's going on in the sky. For example, high clouds usually indicate fair weather. Nimbostratus and cumulonimbus clouds in the lower atmosphere tend to indicate potential for rain. So let's summarize so far. Clouds are aerosols consisting of visible mass of minute liquid droplets, frozen crystals, and other particles suspended in the atmosphere. And I promise I won't read that definition again in this talk. We're familiar with lots of different kinds of clouds, including water clouds, smoke clouds, pollen, dust, sand, and probably more. And clouds tell us a dynamic, a time-dependent story about their environment. They're beautiful and informative, and they have a past and a future. Now, very likely, your first human experience was with clouds on Earth. Maybe you cloud gazed, searching for morphine pictures in the sky. Maybe you used them as a barometer for your day's activities. We all have some experience with them. However, I'm willing to bet that your first, shall we say, cosmic experience with clouds occurred billions of years ago. Pictured here on the left is the constellation Orion. And you can see the four corners that make up the shoulders and the knees and the belt in the middle. And hanging down is the sword. The yellow square around that highlights the nebula that's pictured on the right. This is the Orion Nebula. It's gorgeous, it's stunning. It's a molecular cloud, one of the most well-studied objects of its type. There are too many features to discuss in depth here, but let me point out some of them to demonstrate what we can learn from these clouds. So obviously it's not like a cloud on Earth. It's not made of water vapor. It's not fluffy and white. It's a molecular cloud. It's made of dust and molecules and the stuff of space. It is a massive stellar nursery. It's the birthplace of stars. More than 700 stars have been seen in various stages of star formation inside the cloud, providing clues into this process. And so what can we learn from the stellar nursery? First, notice the shape of the nebula. The gas looks blown away, streamed out towards the edges like a balloon. We can see right here, there's some rims, some regions that look blown away. It almost looks a little bit concave over here as well. The Orion Nebula is extremely dynamic. There's a lot of energetic processes that are happening in it, including star formation. During star formation, stars radiate massive amounts of light and energy that they actually push the gas away. The gas and dust away get pushed away from the star, and they create these cavity-like features that we can see. And so we know just from our eyes, something pushed that dust away. There's a dynamic process happening there. Second, look at the colors. They're the reflections of starlight off of the gas. So think of a neon light, just the ones that you see in a store, an open and closed sign, something like that. The neon lights all have a specific color that comes from the gas that's inside of that tube. The gas creates a specific color of light. And just like that happens in a neon tube, so too the gases and nebula correspond to specific colors and vice versa. The reddish color, maroon color that we can see here corresponds to hydrogen gas. There's massive amounts of hydrogen gas in this nebula. And the blue corresponds to oxygen. And then the dark clouds, the patches that you see right here, well, those are just too thick and dense to let any starlight through, which is a familiar phenomena and something we are familiar with during a cloudy day here on Earth. So to recap here, the Orion Nebula is very much a cloud. It's a collection of visible mass suspended, quote unquote, in a space that's made up of small things like gas and dust that surround the cloud but are too diffuse to see. This nebula is very much a function of its environment. And we can learn all about this marvelous, massive object by its shape, its size, its color, and the things inside of it that drive these features. Its status as a massive stellar nursery provides valuable insight into the process of star formation. So let's talk more about that process for a second. This is a diagram, cartoon diagram of star formation and how we think stars form. We'll start in the top left with a cloud of dust and gas. And over time, over billions of years, gravity between these tiny particles of gas and dust, gravitational forces bring that gas closer and closer together, eventually binding it together with forces so strong that nuclear fusion starts and the core of a star is born. And this is the beginning of a star, a protostar right here, right at the center. The gas and dust then that are left behind that didn't go into the star, we think we think the gas follows a similar gravitational collapse but only this time into planets. And we end up with stellar systems very similar to our solar system, where you have a single star and planets that orbit it. But this fourth step is particularly interesting, partially because it still has some clouds. So I want to dive a little bit deeper. Okay, so after a protostar forms, or a baby star, it's thought that planets form from the disks of dust that are left over. Planetary formation is a process that is still not well understood, but astronomers have recently gotten images from the last few years, and those images are beginning to provide observational evidence for the formation of planets out of the dusty protoplanetary disks that are left over from the cloud of dust and gas that birthed a star. So this picture that you see right here is a grid of protoplanetary disks taken with the Atacama Large Millimeter Submillimeter Array, which it's a collection of 66 radio telescopes, so telescopes that look at radio light, and it lives in the Chilean Andes Mountains. And all of these telescopes collectively look at the sky in radio light wavelengths, and they created these images. They got these images. These are actual objects in the sky in the Milky Way galaxy. So what you're seeing in the orange and red colors are rings of gas surrounding a star at the center of it. And you'll notice that there are these dark rings additionally around these. And it's thought that the dark rings are paths that are carved out by forming planets, as gravity within what originally was a solid disk of gas began to bind together small dust grains and then snowballed them into larger and larger bodies as they orbit the star and eventually become a planet. And so this is one of our first direct observational pieces of evidence for potentially how planets form. So this being one of the major theories of planet formation, then we can see that from the nebula cloud came the star cloud, and from the star cloud came the planets, and on the planets are extra clouds and more clouds. So let's look in at more planetary clouds. This is Venus. This is the second planet from our sun. The atmosphere on Venus is about 96% carbon dioxide, 3% nitrogen, and there are trace amounts of other gas, including oxygen, sulfur, hydrogen, and fluorine. The entire planet is covered in thick layers of clouds such that we can't even see the surface with visible light. The picture on the upper left and the lower right, totally opaque. That's all atmosphere and clouds. None of the surface can be seen. The image of the surface on the upper right was actually taken with one of the Venera probes. And the Venera probes were a series of Soviet Union spacecraft that were designed to study Venus from the 60s through the 80s, 1960s through the 1980s. And after the spacecraft landed on the surface, it traveled through the atmosphere, it landed on the surface, they survived less than an hour before they broke. The surface of Venus is about 700 degrees Fahrenheit. And so anything that lands on that surface can't survive it very long. We were lucky enough to get pictures from the surface back as soon as we did. And the cloud cover that you can also see in this picture, it's so thick that solar panels wouldn't even be able to collect enough sunlight. It's just like a very overcast, cloudy day that we have on Earth, only it's like that on Venus all of the time. Now, the upper atmosphere of Venus also exhibits really, really, really crazy winds, up to more than 200 miles an hour on the very surface. These winds are so fast that they circle the planet in just a few days. Now, the planet itself takes about 243 Earth days to rotate on its axis. So about 2/3 through a year on Earth, this planet has only rotated once. And so these winds and these clouds, they circle the atmosphere in 4 to 6 Earth days. These winds circle the Venus around 40 times before the planet even rotates once. It's insane, the kinds of winds that are on this planet. There's another planet that has really crazy winds in our own solar system, and that's Jupiter. And we see much different cloud phenomena. And there are, again, far too many to go into detail here, but here's some really interesting ones. There's a complicated structure of cloud layers that planetary scientists think exist in Jupiter. At higher altitudes, clouds of ammonia ice exist. And then lower down, there's ammonium hydrosulfide clouds. And below that, there's perhaps water, maybe. Jupiter, we're still learning about that planet's atmosphere as well. The cloud colors relay information about their chemical composition via the kind of sunlight that they reflect. It's very similar, well, it's actually the same process to how we know what color things are by the kind of light that they reflect. So plants, for example, are green because they reflect green light. And so too, we can tell what something is made up of on another planet based on the kind of sunlight it reflects. So on Jupiter, darker clouds tend to correspond to denser clouds that are lower in the atmosphere. And then the lighter color bands correspond to higher altitudes where ammonia ice exists and it can scatter more light equally. And then the clouds are banded in addition. That's one of the most famous features of Jupiter. And you can see from this animation, which came from the Voyager spacecraft, you can really see how the bands display the violent nature of the surface layers. These bands are the results of jets streaming in alternating directions across the planet, reaching speeds of up to 250 miles per hour. And you can see visual evidence of the winds with the eddies and swirling structures in the image on the left. You can see lots of little vortexes and eddy currents between the layers of bands on the planet. It's incredibly remarkable. So this plot shows the band structure of Jupiter and how fast these winds and clouds are going. So on the x-axis, you get latitude. So this is the equator of the planet. At minus 90 and 90 degrees, you have the poles. So this is kind of like Jupiter on its side. And then on the y-axis, you have the wind speed. And so the way to read this plot is each different color of line comes from a different observation, one for the Cassini spacecraft, one from Voyager. And it's a plot of the wind speed as you move from the South Pole all the way up to the North Pole. And so what's important to see is just how fast these winds are going. You know, very, very close to the equator, you have wind speeds that are going close to 300 miles per hour and maybe even up to 330 miles per hour, a little bit more north. It's incredible. Compare these to a hurricane here on Earth. Most of these bands exhibit winds on the order of an earthly hurricane. And these winds are made of ammonia and ammonia hydrosulfide. Can't even say that right. These other worlds in the clouds and their atmospheres are truly amazing. And if we lived on them, we would certainly not survive very long because we can't breathe ammonium. So I've shown so far how some of the planets in our solar system are so different by virtue of their clouds alone. And it's astonishing how unique each one is. Now, going from the rings of leftover star-forming gas to fully formed planets is a huge jump. I didn't mention anything more about planetary formation or evolution, and part of that is because scientists are still trying to fill in those details. So while we're learning about our own solar system and the planets in the solar system, we have questions about other star-planet systems in our galaxy. Are planets and other star systems as diverse and as different as ours? Can they offer insights into what they're made of and what their formation and evolution processes are? So I want to spend the last few minutes telling you about how we learn about the atmospheres and clouds of planets outside of our solar system, or better known as exoplanets. So the discovery of thousands of exoplanets over the last 2 decades has fundamentally changed our view of Earth in the universe. As of just a few days ago, there were 4,569 confirmed exoplanets just within the Milky Way galaxy alone, and you can see them on this plot. The x-axis shows their orbital period in days, or how fast they're going around the star. And then the y-axis shows how large they are relative to Jupiter. So anything at 10 to the 0, anything at 1 means that this is a radius of a planet the size of Jupiter. So the boxes show all of the planets in our solar system. The blue square right here is Earth, and the rest of them are all the planets in our solar system in order. The cyan square is, of course, Jupiter. So what you'll notice is that a majority of the planets that we've discovered are totally unlike anything we have in our solar system. Most of their orbital periods are fewer than 100 days or even 10 days, so they're going around their star in just a few days. And then many of them are a lot larger than Earth as well. They all have planetary radii much larger than Earth. So we can start to model these planets and their physical locations and begin classifying them. And the diversity of planetary radii or distance from their star and the range in densities has enabled the field of comparative exoplanetology. So exoplanetology, meaning the study of them, comparative, meaning we're trying to compare them. We're trying to understand if we can fit them into categories, if there are classes of planets that exist in the universe. So I've labeled here some broad categories of these planets. Hot Jupiters are of order Jupiter size, but they're really close to their star and really hot, sometimes 10 times hotter than Earth. Likewise, lava worlds are also really close to their star, but their density indicates that they're likely more solid. And their orbital environment is likely so hot that these planets might even be molten. And then there are planets that have water on them, and there are rocky planets too. And these are pretty broad categories, and we want to know more about these planets. So we can use the transit method to aid in the characterization. And this animation is a good primer for the transit method. What's being plotted is a light curve, which describes the star's brightness as a function of time. The transiting planet passes in front of the star and blocks out starlight. The ingress is the leg when the planet begins to move in front of the star. The flat part of this curve is when the planet is in full transit, and the exit is called the egress. The transit depth is the relative change in the unocculted starlight and is essentially the ratio of the planet and the star's cross-sectional areas, RP over R star squared. So if you have a larger planet, you have a larger planet radius, you get a larger transit depth, and you can detect the signal with photometry with band passes that are tens or hundreds of nanometers wide, and you'll see this effective planet size. But if instead you look at individual spectral features during transit, we can begin to learn about the gases that are in the planet's atmosphere. This is called transmission spectroscopy, and it's a phenomena resultant of the different gases in the planet's atmosphere absorbing some starlight and transmitting the rest. And this animation is showing how the size of the transit depth changes when you observe the transit in different wavelengths. Here we see that 2.3 micron light has the greatest transit depth, which indicates that there's more material absorbing 2.3 micron wavelength light than there is absorbing 2.1 microns. So now not only are you detecting the disk of the planet, you're detecting the presence of these atmospheric constituents, the composition of the atmosphere. Here's another way to picture the transit method, seeing how starlight traverses through a planet's atmosphere. And the amount of light, the quality of it, if it scatters, the color, or if no light passes through at all of that tells us a lot about the atmosphere and the presence of clouds, and even the motion of the atmosphere. And this field of study is wide open, and we've just barely scratched the surface of exoplanet atmospheres. And I bring this up because it's what I do. I actually don't study in depth clouds on Earth or nebula or the clouds of our solar system planets. I actually work on a small satellite called the Colorado Ultraviolet Transit Experiment, or CUTE. It's a small satellite the size of a shoebox, and it has a telescope inside that's designed to look at ultraviolet light. The upper picture on the left is a CAD rendering of the spacecraft. The middle top is an actual picture of the satellite with a solar panel on top of its visible. And then the top right is our silly little logo. And the bottom middle is me and a colleague delivering the spacecraft to the launch vehicle. And the shoebox form factor is referred to a 6-unit CubeSat because you could fit 6 10-centimeter cubes inside of it. And we just launched it in September, about 6 weeks ago. And while we're in space, we're going to point at different planets to try and learn about their atmospheres. And we hope to learn about the atmospheres of them, to learn more about their diversity, how they're formed, if they're changing, and to try to use them as laboratories to answer questions we have about our own solar system. So I started this talk asking you, what are clouds, man? And I hope that I answered that sufficiently. And so now I think the question remaining is, why clouds, man? Why do I love clouds when I study exoplanets and I worked on that satellite? And I have nothing in my day-to-day research to do with actual clouds. And the answer is because I've always been a sky gazer of both clouds and stars, because you can begin to learn about the physical processes that govern our world just by going outside and looking at your daytime sky. Because sometimes studying things so far away from Earth in the universe, like exoplanets, sometimes that can feel lonely or existential, or isolating even. But for me, clouds are grounding, ironically. Seeing earthly cloud processes in other places in the universe, in some sense, lets me learn more about humanity and Earth. Another thing I don't study is the search for life as we know it in other places in the solar system or the galaxy. I don't research astrobiology, but I do wonder what aliens see when they look up at their own skies. Do they see clouds as beautiful and as varied as we do here on Earth? How do other planets form and create clouds? Being a scientist, our research demands that we hone in on minute details to answer specific questions. But those details are always connected to other phenomena both in the universe and of ourselves. From clouds we came, and to clouds we'll probably go. Candace had it right when they said that all we are is dust in the wind, but maybe it's more like all we are is clouds in the universe. Thank you.
Thank you, Erica. Wonderful talk. If you want to turn your screen share off, we can get to some Q&A. While I am asking you some questions, I'm going to let some questions fill in the YouTube chat. But I want to start by asking you about you, because AOT at the end of the day is more about interacting with scientists than it necessarily is about science itself. So I wanted to ask you some stuff about yourself. First thing, what are your hobbies like outside of astronomy?
So I donate blood a lot. I like to run. I like to read. I have dabbled in winemaking as well. A little bit of woodworking. And I like to think a lot.
Fair enough. I think we all do. That's why we're scientists. So I wanted to ask you about you said you got a philosophy degree as well when you were in undergrad.
Mm-hmm.
What made you want to do both at the same time?
Because they're both different ways to answer the question why. So the natural sciences started out as philosophy, and it was people just sitting around being like, why is a cloud, man? Like, what makes that happen? And so they're both develop different and complementary critical thinking skills that allow you to evaluate and answer different questions, or at least figure out how to go about answering some of them. So philosophy can touch more on things that we don't yet have data for or research for, or even know how to begin an approach. And it can also help us understand our place in the world a little bit more. So if you think of existentialism, for example, that's a field that has a lot to do with understanding meaning, understanding humanity. And I found that really complementary towards me wanting to learn about the universe. And then I liked physics because it was the gateway to astronomy. And I liked astronomy because I had a book about aliens when I was in third grade that I really, really liked. It was like this learn to read level 4, all about aliens and little green men. And I read that book so many times. And I was like, man, aliens are cool. I hope I get to see one day.
Do you believe in aliens?
Oh, yeah. There's definitely life somewhere else.
Okay. That's what I've always said, but I just always like to ask.
Mm-hmm.
Okay. And then the last question about you yourself. What is your favorite Pokemon?
I don't know, man. I never played Pokemon.
Okay. Well, we always ask because Tabby's son Jude really likes for us to ask. But I would like to suggest to you, if you ever do play, that you should pick yourself up a little Wooper. And yeah, that's my shameless plug for Wooper. Okay, so on to some science questions, and I am going to ask you the first science question as well, because I can do that because I'm running the show. Can you, two famous clouds that you didn't talk about that I want to know your take on is the small and large Magellanic Clouds.
I don't know that I have a take on them other than I think they're really pretty and I wish that I could see them in person. Like I said, I don't study nebula for my research at all. I just think they're beautiful and amazing. And they're the things that people look at that like inspire them to want to learn more about space.
Right.
Yeah.
Right. Okay. Well, our first question from the audience is from Stephen Dorsher, and he asks, are the stripes in a disk where planets form due to a similar principle in breaks of stability of wind speed like they are with Jupiter?
Kind of. So what we think happens when these little planetesimals start forming is you have these little clumps of dust and gas that are all forming around, and they start clumping together and creating little things. And then they gather more and more stuff, and they eventually start clearing out stuff. So as these clumps get larger and larger and larger, there are collisions that are happening from the gas that sometimes help accrete more matter onto that planet, or they fling it away. So it's not so much instability as it is just mass being accumulated and cleared by this massive body.
Okay. Isn't that also part of the reason why Pluto is now classified as a dwarf planet? Because it doesn't clear its path?
That I am not sure of. Yeah, that I am not sure of. The best visual example that convinced me why Pluto wasn't considered like a main planet in our solar system before was putting it in context of all of the other bodies that are orbiting the sun as well. And there are hundreds of them that are way, 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 outside of the orbit of Pluto. And you look at Pluto in the context of that and you say, man, that's not really a major planet, is it? It is kind of more of a planetesimal orbiting the sun.
Yeah, it kind of looks like all those other ones like Ceres, huh?
Mm-hmm.
Okay. I will ask you another question, and that is, so exoplanets are a field that gets a lot of media press, and whenever you see an article, there's almost always an artist rendition of that exoplanets, and sometimes they show cloud structures. What do you think about that? Like, are those informed by science, or are they just an artist's interpretation?
We do have some evidence for what we think are clouds on exoplanets, and that comes from different scattering patterns of the starlight bouncing off. So just like Earth has its own atmospheric structure, there's, troposphere, mesosphere, stratosphere, ionosphere, things like that. Other planets also have structure to their atmosphere that we can tell by looking at the planet, both in transmission, like the examples that I showed, but also by looking at the reflection of starlight. So when the planet is on the side of the star, it's actually reflecting sunlight back to us. And by combining transmission and reflection spectra and looking at it in infrared and optical and ultraviolet wavelengths, you can begin to probe these different layers of the atmosphere. And so, not that we've ever actually had direct observational evidence for clouds and exoplanets, but you can model what clouds versus a hazy atmosphere versus total cloud cover would look like, and compare what your models say to what our observations actually are. And so there's some evidence that suggests, this planet might have a lot of clouds on it.
That makes sense. All righty. I think that is all of the questions that we had in the chat, but you did get quite a lot of compliments on a wonderful talk in the chat if you wanted to. But so for now, we're going to break for an intermission. Before we do, I would like to ask all of you watching one more time to consider donating to our PayPal, and remember that we don't have Venmo anymore. If you do, let us know in the comments which of the solar system's 4 ringed planets is your favorite. That would really help us out. So we are going to take a quick break, and we will be back at 7:45 p.m. Alrighty, welcome back, everyone. It is 7:45, so we'll get ahead and start going straight into the second half of our show. So our second speaker today is actually an LSU alumni and even graduated from the same group that I'm currently researching in. He's now a postdoc at Western University in what he calls fake London, aka London, Canada. Outside of work, he says he enjoys running and bouldering and says he once ran a 100K, quote, on a whim. So he's here to talk about whether or not there is life on Mars. Please help me introduce Kundan Kadam.
Hello, everyone. So okay, let me share my screen. All right, here you go. So yes, as Courtney said, I'm Kundan Kadam from Western University. And today I'm going to talk about life on Mars. So just a disclaimer that I don't really study Mars. I actually study star and planet formation from a theoretical point of view, but I'm just fascinated with Mars and prospects of life on it. So let's see. So I'll be talking about Mars in terms of astrobiology. So astrobiology means applying principles of biology to the universe, and it pertains to questions like, are we alone in the universe? And if there's life, in what condition that may arise, and so on. So it's a very interesting topic. So let's go to the beginning. Initially in the last century, when the telescopes were invented and so on, astronomers looked at the red planet, and what they found was these structures. So these are drawings made by hand, because at that time there were no cameras. And these drawings are by Percival Lowell. So that was an American astronomer, businessman. And what he drew was these straight lines or canal-like structures. And he really believed that there was a civilization on Mars which was dying because of lack of water, basically. So these are irrigation channels. And he really pushed that idea, but of course now we know that this is not true. And Mars doesn't really have a civilization. But we do see this dichotomy between the two hemispheres. So here you see that the northern hemisphere is flat and the southern has a lot of structure. So there are a lot of theories about it, but one of them is that an impactor, a giant comet or a protoplanet impacted Mars in its early evolution, and that shaped the geography of the surface. So the northern part of Mars is about 3 to 5 kilometers thinner than the southern hemisphere. But we are here to talk about life, not geography. So concept of life on Mars is an old idea. It's also in science fiction. So on the right, here there's one of my favorite science fiction books. It's War of the Worlds. So the poster shows a news article from 1938. So what they did was they broadcasted a story as if it was a real news event. And in the story, what happens is that there are explosions on Mars. And then there are spacecraft landing in New Jersey. And these aliens come out of the spacecraft and they start shooting. But people actually did believe that in real life, and they started driving out of the city, and there were traffic jams and so on. So US bans fake radio alarms. So that's the story. And on the left-hand side, it's one of my favorite book series, which is a Mars series by Kim Stanley Robinson. So red, green, and blue Mars. So in the red Mars, he talks about colonization of Mars, and then terraforming and long-term consequences. So if you're interested in science fiction, these are some very good reads related to Mars. So in terms of real evidence of life on Mars, there was this, you must have seen this image. This is the evidence of fossil life in a meteorite from Mars. So what happened is that about 17 million years ago, that's what we think, a comet or some kind of meteor impacted Mars, and it dislodged a piece of its surface or rock. And that piece went into space, and at some point about 18,000 years ago, it landed onto the Earth. And this was found in 1984 in Antarctica, the meteorite. And in around 1997, the scientists found these structures. So these are microscopic structures which look like bacteria. And now we know that these are probably not bacteria. These are geological in origin. But at the time, even Bill Clinton talked about it on national television. So in case we find alien life, we don't define it in terms of where that organism is. We define it in terms of how it's related to the life on Earth. So on the Earth, we have these big domains of life. These are called, one is bacteria, one is archaea, which are small unicellular organisms just like bacteria. And then we have eukaryotes, which are like the big animals or trees that you see. You see the kingdom, Animalia and Plantae and so on. So the theory is that all of them had a common ancestor. So this is called primordial ancestor. That's because all of these forms of life, they have a DNA-based life, and they have a water-based cell structure and fat-based membrane and so on. So they have certain commonalities. So in case we find life on Mars, we have to decide how it's related to the life on Earth. And there are some hypothetical biochemistry that's possible. One is silicon-based life. So even on the Earth, we find these diatoms. So these are basically plankton-like creatures in the sea. And these are plentiful. So it's like 20% of the oxygen is created by these diatoms. And the funny thing is that they have an exoskeleton made of glass. So they incorporate this silicon into their biochemistry, and they make these beautiful structures. So silicon has a chemical structure similar to carbon. That's why it's possible. Now, what can life on Mars tell us about life on the Earth? So there's some theories of origin of life. This is called abiogenesis. So one of them is life originated outside of the Earth. So that's the extraterrestrial origin. And one is terrestrial. That means it's native to the planet Earth. And in terms of extraterrestrial origin, we have random panspermia. That means life came to Earth via comets and asteroids and things like that. And directed panspermia basically means aliens. Someone inseminated the Earth. And in terms of terrestrial origin, we have inorganic origin and then organic origin and so on. So I won't go through the whole diagram in detail. But in case we find life on Mars, we have to decide how it's related to life on Earth. And that will give us a clue on what might happen in the rest of the universe. So on Mars, well, we have already contaminated Mars. So if you ask the question directly, is there life on Mars? The short answer is yes. And the life is called bacteria. So this is the Curiosity rover. So it's a selfie, which is obtained by stitching a bunch of images taken by its camera. So the bacteria are, basically the contaminants, and there are about 300,000 of them. So they are not on the surface. They are in like cracks and crevices on this rover. And they are dormant, basically. They are not reproducing. And everything on the surface is basically sterile because of the UV radiation. But it's possible that maybe in the future, if you have enough water, they might get activated again. But in current missions, we make a point to decontaminate everything so that we don't spoil the biology on this planet. So in terms of requirements for life, so the life needs energy, which is common in the solar system. We something like light energy or chemical energy. So even at the distances of Pluto, which is about 100 astronomical units, that's the distance between Sun and the Earth, there's enough light to sustain life. So unicellular organisms can have enough energy to sustain at that distances. We can have carbon, which is plentiful, and certain elements like nitrogen, phosphorus, sulfur, and so on, which are needed for the biochemical reactions, like catalysts and so on. These are also likely to be common. And what's rare is actually liquid water. So water is found at on several planets, but it's mostly in the form of ice, and that's not useful. So this is the reason that whenever there's a discovery of water or ice on, let's say, Moon or any other place, it's such a big deal because this is the main things that's not common, and it's essential for life, which is similar to what we find on the Earth. So in terms of getting liquid water, there's this concept of circumstellar habitable zone. So is the distance from the sun at which the water can be in its liquid state. If you're too close, the water will boil off, and if you're too far away, it will just freeze. So Earth and Mars, both of them are in the habitable zone. But as we shall see, Mars doesn't actually have liquid water right now. So in addition to being in the habitable zone, the planet also needs to have a Goldilocks size. So what does that mean? So if the planet is too small, let's say the size of the Earth's moon, all the atmosphere that's on the surface, it will just boil off. And all the surface water, it will eventually evaporate and also boil off. So in order to sustain an atmosphere as well as liquid water, you need to have certain mass of the planet. Otherwise, it will be just a barren surface. And the size also decides the geology of the planets. For example, on the Earth, there are plate tectonics and there's volcanic activity and so on. So that sustains the geological carbon cycle. So the volcanoes and so on, they spew carbon dioxide into the atmosphere, and then you can have a thick atmosphere. So Mars doesn't have any plate tectonics. And another thing that the internal geology offers is the magnetosphere, so which protects the Earth from harmful radiation of the sun. So these are basically charged particles which emanate from the sun, and they're deflected via the magnetic field lines. So the Mars doesn't have this protection of its magnetic field. So essentially what happens is that all the atmosphere, it gets eroded, and there's also no ozone layer, so all the radiation gets to its surface, and it's a double whammy. So it's bad for life. So apart from the circumstellar habitable zone, you can also have habitability on the satellites. For example, all the big satellites of Jupiter, Saturn, Neptune, and satellite of Pluto as well. It's possible to have liquid water, because essentially what happens is that if the planet is close enough, or if the satellite is close enough to its planets, it basically gets gravitationally squished and compressed, and that sustains liquid water through the tidal effect. So there's enough heat for water to be liquid. And two of my favorite satellites, one is Saturn's satellite Titan, in which we landed Cassini-Huygens probe in 2014 or something. So that's the image of the surface. So it's very cold. It has methane lakes and so on. But it's possible to have a different kind of biochemistry on Titan. And my second favorite is Europa, which is Jupiter's moon. So it's thought that it has an ice surface, but underneath the ice, there's a large ocean, and it can be so large that it contains more water than the water on the Earth. So these are two fascinating satellites that we have. So coming back to Mars, we know that Mars has or used to have water because of satellite images, as well as the probes and the rovers that we have sent. So this is the Mars satellite that was sent in, I think, 97 or so on. So you see these big booms. So these are like 40-meter long antennas. So these are ground penetrating radars, and you obtain images like this. So the polar caps that you see on Mars, so these are basically CO2 ice. So that's carbon dioxide, but it's thought that underneath the carbon dioxide, there's solid water. So that's water ice as well, because hydrogen is what the images reflect. So in addition to the poles, there's also evidence for erosion on the surface due to water. So these structures, these look like enormous outflows, which may be caused by floods, river valleys, deltas, and lake beds, and so on. So which suppose the Mars ocean hypothesis that at some point the northern lowlands that we saw earlier, it was entirely underwater, and about 1/3 of the surface was covered by water. So that's the ocean hypothesis. And in recently, I think 2007, this is the Phoenix lander. So the lander had, no wheels, of course, but it had a scoop, and it scooped the surface. So it found ice right below the surface. So still no liquid water, but it had water ice. And Curiosity rover, which went there in 2013, so it found these pebbles or cobblestone. So you might ask, what's so special about these pebbles? But these rounded structures, they need to be formed cowed by friction, and something that can provide this friction is flowing water. So we think that it was a riverbed at some point. So what we know for sure is that today water exists only as ice or water vapor. It exists well below the ice caps, and throughout the surface, it exists as subsurface level. And if you melt all of the water, it covers the whole planet to a depth of about 35 meters. So that's a lot of water. I was surprised when I learned about it. So, so far we have sent several missions to Mars, so we have 10 satellite orbiter missions. We have 5 landers, 5 rovers, and we also have a sample of Martian meteorites, but none of them have evidence of life so far. But earlier this year, this rover Perseverance, which landed on Mars, so it's specifically designed to detect life on Mars. So let's look at what this rover will do. So I like this chart because this is just a plaque on the rover, which shows the rover family, which is sent to the Mars. So these are the 5 rovers that were sent. So this Perseverance, it will land in this region in the Jezero crater. So this is very interesting because here you can see this is a crater, ancient crater. So this is like, 8 miles wide. And here you can see an inflow channel of something like a river. You see an outflow channel here. So this entire thing was a lake at some point. And here you can see a nice river delta. And this is exactly the place on Earth where you can find evidence of life. So if you have like a rainforest or something, everything that gets washed through the river, it gets deposited here and it gets sedimented. And this is very interesting to follow. So this is how it looked like about 4 billion years ago or 3 billion years ago. This is an artist's rendition, but funny thing is they forgot that the temperatures were too cold even back then. So this must have been covered in ice. So the lake was probably subsurface. So one of the interesting instruments on the rover is a Sherlock. So it's basically a spectrometer. So what it does is it's located on one of the arms, and it's a no contact instrument. What that means is if the main camera detects something interesting, you put this spectrometer near that stone or rock, whatever that is, and it shines a UV laser. The laser reflects and comes back, and you can detect its spectrum. So what it's looking for is potential biosignatures, so organics or minerals. And if it finds something really interesting, it can actually take a sample of that thing, So it has an arm with a drill bit, and it can take a sample of the size of a lipstick, 1/2 inch by 2 inch wide, and it can take about 42 of these samples. It measures them, takes images, and stores them in an airtight container. So it's basically a sterilized compartment, like a tube. And the most interesting thing is that it drops them for retrieval by later missions. So this is the first time in which there's a possibility of getting a return sample of Martian surface. So in 2031, there's this Mars sample return mission, which is still a concept. You can see here, this is like artist's rendition. This thing doesn't even have legs, so I don't know how it will find the samples, but that's there you go, I guess. There are plans to do sample retrieval. And what we look to find in these samples is something like this. So this is evidence of fossilized microorganisms on the Earth. So on the left, you see black shirt rock. So this is basically a very fine rock in which you find sediment, so it's really hard to drill. But if they're fossilized bacteria, you expect to find them in this type of rock. And on the right-hand side, you have something called stromatolites. So these are colonies of bacteria which grow on the surface underwater. So you have one colony which is like a mucus-like membrane, and another colony grows on top. And at the end, if it fossilizes, you find these wave-like pattern with lumps and bumps, and this is what we expect to find. So in addition to finding signatures of life, it also, this particular mission, Perseverance, it is testing for manned missions. So one of the ideas it's testing is materials which can be used for spacesuits. So polycarbonate glass or Teflon, things like that. So these are located like on a plate on its body, and it will see how these different materials behave in the Martian atmosphere. If there's erosion, if there's a chemical reaction, and it will test these not just visually, but also through the spectrometer. So we will know exactly how these materials behave, so that future astronauts or Martian people, I guess, for their protection and for their spacesuit. So another interesting instrument is MOXIE, which is basically which creates oxygen through reverse electrolysis. So this is a very expensive process. You have to shut down everything else and divert electricity to this. But it's a very important experiment because if humans ever go there, we'll need oxygen. And also many times if you need to launch something off of the surface of Mars, if you use chemical energy, you need to burn fuel, and to burn fuel, you need oxygen. So oxygen is very important. It's really expensive to take it from, bring it from Earth. And the rover also had this helicopter, which was Ingenuity. It's just a test bed of how we can have a drone on another planet. So it was really difficult because Mars has only 1% of the atmosphere. So you can see the power to weight ratio has to be really high, but this thing did fly, and this is very exciting because now we can explore alien planets or planets in our solar system with something like a drone, and that'll be very fast and efficient. So I'd like to end this talk with, this view of sunset and during the day on Martian surface. So if you ever go to the Martian surface, it will be very eerie because sunsets will be blue, and at the daytime it will be red. So this effect is due to scattering in the Martian atmosphere due to the dust. So in the daytime, the dust scatters the sunlight, and you see all the red. But during the sunset, all the red light is scattered off. So whatever remains is the blue light. That's why you see the sunset there. So with that, I'd like to conclude the talk. So in summary, what we learned is that, Mars had liquid water in the past. There's no liquid water now. We haven't found any biosignatures of life there yet, but we are looking into it. And hopefully we'll be able to answer hard questions of life. So with that, I'll end this talk, and I can take any questions if you may have.
Perfect. Thank you so much. It was a wonderful talk. If you want to stop sharing your screen, then we can get the Q&A going. Right. So I'm going to ask you some questions about yourself as well. Oh, really? You don't get out of it or anything like that. The first question I want to ask you is, do you miss Baton Rouge?
Yeah, very much. Yeah, it was amazing times. So I graduated there in 2017, and some of my best times I had it in Baton Rouge. Really nice people, nice food, and, things like that. Miss it a lot.
Definitely some good food. But anyways, I wanted to ask you, what got you into astronomy?
Well, it's maybe a cliche question, cliche answer. But I was into dinosaurs when I was a kid. And then I read this Time Machine book. I forgot it's by whom. But so then I had two possibilities to study dinosaurs, or invent a time machine and go back in time to study dinosaurs in real life. So I decided to join physics to invent a time machine. And I realized it's not possible, but I found astronomy fascinating, so I stayed.
All right. Yeah. We actually, Allie, who's one of our streamers, we have a joke that it's the dinosaur to astronomy pipeline. It definitely exists. It's a real thing. Um,
I agree.
what is your favorite part of being an astronomer?
It's fun to a job to do. It's fun to talk about it. You love your job, so that's a good thing.
Yeah.
And it's interesting. You can many times you have freedom to choose whatever interesting project you find. Whatever project you find interesting, you just talk to your advisor. Hey, this topic looks interesting. Shall I investigate? And many times they are supportive, and you just go ahead, read papers, and make some contributions. So, and you get paid for it. So, yeah.
Yes, definitely. That's the important part, huh? Okay, and then the last question about you. What is your favorite Pokemon?
My favorite Pokemon is what's that? Shocked Pikachu face. Pikachu is the only Pokemon I know. I don't know anything else from Reddit, I guess. But yeah.
Shocked Pikachu is a very good meme. Very good. Okay, so I will ask you the first science question as well. Do you know anything about possible life on other planets, or was all of your research for this just with Mars?
So we don't really know, So personally speaking, I think the first biosignatures would come from exoplanets if we are able to resolve their atmospheres from something like James Webb Space Telescope. If you have oxygen and like other biochemistry detections from other planets, but most likely it will be like microbial life, which is affecting the whole geological structure or atmosphere of the planet. That's my opinion, but we don't have any evidence for that.
What about the recent like Venus observations?
I think that might be an anomaly, but you never know. So we have a sample size of 1. That means we only have our own biochemistry to work with. So unless it becomes a consensus in like astronomers that it actually is life, then just one paper or a couple of papers, it doesn't say much.
Okay. Erica is in the chat saying Venus was a false signal. So
maybe, yeah, I agree.
Okay, so our first question from the chat is from Angelica C. And they ask, what if other life forms don't need the exact same circumstances as life on Earth? For example, what if life doesn't need liquid water or heat?
That's a good question. So it's possible that it's methane based. So the other hydrocarbons can also act as solvents. If it's really silicon based, if it's not carbon, what that means is all the reaction would occur so slow that you'd look at a rock and you wouldn't think that it's alive, but it's actually alive and it's evolving over thousands of years. So that's also possible. So short answer is that we won't know really until we look at it.
Interesting.
Until it tries to eat us, I guess. But
could it even like really move that fast if the reactions were going slow?
Not that one, but the other one behind you, I guess, something like that.
Fair enough. Okay, and the next question is from Stephen Dorsher, and he asks, I initially read that Perseverance was drilling for shallow surface ice, and the first drill didn't find it, but they hope to find it later. Do you know if they found it yet?
I don't know, but I think they have 42 sample tubes, so they have more than enough chances to go around and look for interesting places. And the mission is for several more years, so definitely I hope they'll find it.
All right, and I have one more question for you as well. You mentioned that the rovers do bring bacteria from Earth to Mars. Do you know how long they live there?
I read it. It's shocking. They live about 10,000 years or so. So they are not reproducing, they are not multiplying, but if you don't touch them, they'll be there for like thousands of years.
Interesting. Wow.
Yeah, they're very hardy.
Okay. Well, alrighty. Well, thank you for a wonderful talk, and then thank Erica as well for another wonderful talk. That is all the questions that we have from the chat, and we are out of time. So I'll just go ahead and thank both of you very much, Brendan and Erica, for very wonderful talks. We know you're both really busy, so we're really thankful that you guys came out. I also want to shout out to our streamers, Allie and Alex, who are behind the scenes, and they work really hard to put on this show for us. Before we head out, I have a few more things I want to mention. If you're watching us asynchronously and not live, please feel free to interact with us. So subscribe to our channel, try to get notifications for our next show, be sure to like the video. All this stuff is great. Tonight, there is going to be a lunar eclipse, so definitely make sure you go outside and watch it if there are no clouds in your area. And then lastly, keep an eye on our Facebook, Instagram, and Twitter, where we post about all of our events as soon as we have information. And I'll see you here next month on YouTube. Our show is on the 16th of December, and we will have 2 speakers. They're going to be great. So thank you all very much.